All right. Good morning, afternoon, or evening, everybody. Welcome to the NASA Commercial Satellite Data Acquisition Program Vendor Focus GHGSat webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we're going to go ahead and get started here. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is please enter those into the Q&A panel rather than the chat. And you should see this located on the right side of your screen. Today's webinar is being recorded. The recording will be posted to the CSDA program playlist within our NASA Earth Data YouTube channel within a week of completion. Once completed, what I will do is I'll send an email to all registrants and participants that includes links to both the Joseph, if you could address any questions in the chat, that would be great. I'll send an email to all registrants and participants that includes links to both the recording and also the presentation slide decks used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour long with 45 to 50 minutes allocated to the presentation and live demonstrations. A 15-minute Q&A period will follow, and depending on the volume of questions we receive, we may extend the Q&A period an additional 15 minutes from end time, but with a hard cutoff of 3:15 p.m. Eastern. During this afternoon's webinar, we will have one CSDA program speaker and two speakers from GHGSat to present the vendor content. Dana Ostrengo will be our first speaker excuse me, this afternoon. She is the NASA CSDA project manager here at Goddard Space Flight Center. She'll kick us off with an introduction to the CSDA mission and program goals and provide a brief overview of the NASA CSDA GHGSat contract and data access. From there, we will transition to our GHGSat vendor speakers. Our first speaker for this afternoon from GHGSat is Tanya Harrison. Tanya is a senior science advisor with GHGSat. She will begin with the vendor content portion of today's presentation, providing a brief overview of GHGSat. From there, she will introduce the methane data products that are available through NASA's CSDA program. Once finished, we will transition to our second GHGSat speaker, Dylan Jervis. Dylan will speak in depth to the platforms and instrumentation methodology. Once finished, we will transition back to Tanya for a quick discussion of GHGSat methane data use cases, and finally, we'll wrap up by highlighting data services available to support end users. Once finished, we'll then move to the optional final polls and open up the question and answer session. We do have two technical subject matter experts from GHGSat supporting this afternoon's Q&A session. Our first is Lars St. Pierre. He is a customer success manager at GHGSat, and Johannes Loschnig, a senior technical advisor. Before I toss it over to Dana, what I want to do is say a couple of words about this afternoon's Q&A session. We will try to answer all of the questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. And just another quick note, I noticed a comment about the polling questions. I can open up that same set of polls a second time, so I'll do that in just a moment. So with that, it is my pleasure to introduce today's first speaker, Dana Ostrengo. Dana, and I'm going to stop sharing my screen here and toss it over to you. All right, so Dana, you should have presenter privileges at this point. And I'm going to open up the polling questions again for everybody, so thank you.
All right, thank you, Jennifer, for getting us started today. Can you see my screen?
I can see your screen, thank you.
Great. So welcome again all to the Commercial Satellite Data Acquisition Program webinar series. We're here today to learn about GHGSat. I'm Dana Ostrengo, I'm the CSDA project manager at Goddard Space Flight Center. If you missed any of our previous webinars, just to give you a little bit of background about CSDA, we are the Commercial Satellite Data Acquisition Program for NASA. We have a mission to focus on identifying, evaluating, and acquiring commercial satellite data that supports NASA's Earth science research and application goals. So the program has 5 main goals. One is to establish a continuous and repeatable process to on-ramp new commercial data vendors. Two is to enable sustained use of the data for broader dissemination to our scientific community. We also want to ensure long-term data preservation, access, and distribution of that data, ensuring scientific reproducibility, and to collaborate and partner with interagency and international partners on the evaluation and scientific use of the data. And then last, to comply with the 2003 US Commercial Remote Sensing Policy. If you missed any of our previous webinars, we do have a YouTube channel listed here, and you can go ahead and visit any of those previous recordings. So we completed our last IDIQ on-ramp 1 back in September. This is a multiple award on an indefinite delivery, indefinite quantity fixed price contract that was in response to an RFP that closed in March earlier last year. The contract goes through November 2028. We awarded 8 new vendors under the IDIQ on-ramp 1, which includes BlackSky, ISci, MDA, Pixel, Planet, Satellogic, Teledyne Brown, and the Tomorrow Company. So these 8 new vendors join our previously awarded 7 vendors. So this means now that we have 15 active vendors on contract under the IDIQ. And when they come on to our active contract with CSDA, the CSDA program will evaluate their data, and then once complete, they'll be able to propose to competitive task orders. So if they're previous vendors that we held a BPA agreement, they have already been evaluated and they can now compete under the IDIQ. So we have 2 types of contract vehicles. Right now we are moving away from our blanket purchase agreements in favor of our IDIQ contracts. So everything now is starting to move into that IDIQ space, and where we allow a more competitive environment for our commercial vendors. We've been building upon our collaborations as a program with our federal partners as well as our international partners when it comes to data assessments, looking at new capabilities and data sharing. We're also working to create a more efficient search and discovery of our data within our program for authorized users through our own program portal, but also integrated with the NASA Earth Data Search client. So you can search for data across all of NASA's missions along with our commercial partners. Our program is heavily focused on the continued assessment of the quality and utility of the data. So just looking at all of our vendors listed here, in a reverse timeline order, we have kicked off the evaluation of Planet IQ and Umbra Lab data. We just passed our midterm evaluation point. We have been having discussions with the PIs and have our SMEs currently conducting evaluations of their data. We have 4 evaluations that are at or nearing completion with the BPA on-ramp 3 solicitation. GHGSat evaluations have just been released as of yesterday, so that is perfect timing. You can get those available on the CSDA website under the GHGSat portal page. We are also in the process of releasing the publication soon for GeoOptics, Capella Space, and ISci. They've all completed evaluations and had their debriefings, and final points will be made soon. The data that was acquired during these assessment periods are also available through the SmallSat Data Explorer, which I'll go through in just a moment. We've completed the evaluation process for BlackSky and Airbus, which were part of our on-ramp 2 solicitation a lot earlier. And we have DSIS and EarthM data that was brought in through our pilot program and as part of our cooperative agreement. We also have brought in Planet Lab data, Inspire data, which was part of our early on program creation, and have continued the ingestion of that data for data continuity. So we're continually pulling Planet and Inspire data on a regular basis. We also acquire Maxar data via our partnership with NGA, but also through our own contract for data that's offered specifically to CSDA. So GHGSat, which we're here to talk about today, has been part of our program since September 2022, when they were previously awarded a blanket purchase agreement to acquire emissions data for the purpose of evaluation. The evaluation provided not only a full assessment of the GHGSat data, but also facilitated 2 new guidelines for quality assessment criteria for emissions and atmospheric column data. In September 2024, GHGSat entered into an IDIQ contract. They were awarded a 24-month task order as part of a competitive process in February of this year to provide emissions data for research and application programs. The data that's acquired under this task order is available to all our authorized users through our SDX interface. And if you qualify for access with our licensing agreements, you can get authorization through the CSDA web form. You can see here a screenshot and link to our Satellite Data Explorer, where you can search and access not only data from GHGSat, but also data from our other partners. Data that is downloaded will continue to be integrated and available through this interface that's constantly being updated. And as I mentioned, we are currently integrating data to that Earth Data Search client. So that brings us to the next portion of our webinar. Please welcome again our invited speakers who will talk to you about GHGSat. And I'll stop presenting, and Tanya, you can take it away.
Thanks so much, Dana. Let me pull up my slides here. Okay, great. Thanks so much. Thanks everybody for joining us this afternoon. Like Jennifer said, I'm Tanya Harrison. I'm Senior Science Advisor at GHGSat, and my background is in remote sensing, and I used to work in mission ops for a few different NASA missions. So now I'm on the other side with industry, and Dylan Jervis is joining me as well, who is a senior scientist who's going to dig into a lot of the technical details of the data and the calibration process. But for folks that aren't familiar with GHGSat, we'll do a little bit of an intro of the constellation and the data products that are available, then get into the super technical details for the folks that really want to nerd out about that, and then talk about how to actually apply for access through the CSDA program and leave some time at the end for Q&A. So GHGSat is a leading edge space and data company founded in 2011 in Montreal. And we provide actionable metrics and insights through advanced emissions monitoring solutions and analytics tools. The team is about 160 people, including engineers, scientists, data analysts, and sector specialists. And we launched our first prototype satellite called Claire in 2016, growing to a constellation of 10 methane monitoring satellites and 1 CO2 monitoring satellite at this point. We do global point source emissions monitoring. So we are looking at individual sources of emissions, and we'll get into details of this later. And we do this mostly through satellites. We also have some airborne sensors as well. We won't talk about that too much today just because they're not included in the CSDA program. But this data is really geared toward looking at emissions from individual sources like oil and gas facilities, landfills, and coal mines, just to name a few examples. So right now we have 10 methane detecting satellites in space with a spatial resolution of 25 meters. And we operate in the spectral range of 1630 to 1675 nanometers. So this is a very intentionally narrow range to really hone in on that methane signature. The spectral resolution is 0.3 nanometers, and we have a detection threshold for onshore sources of 100 kilograms an hour and offshore of 150 to 1,000 kilograms an hour, depending on season and latitude for a bunch of different factors. The detection threshold is the 50% probability of being able to detect a plume if the wind speed is 3 meters per second. The field of view of the satellites is 12 by 12 kilometers, and the revisit time across the entire constellation is about 1 to 2 days. Like I mentioned before, we're a target mode satellite, so we only take observations over specifically tasked locations, as opposed to a broad area mapper that you might think of for like a Sentinel-5 Tropomi type instrument. So how do we actually go from the observations to a methane quantification? We start with observation planning with you as the user, getting the coordinates of the spots you're interested in, and okay, so we start with observation planning with you to get your lat/lon and the time ranges for the spots that you want to observe. And then we run algorithms on our end to do the optimized planning to determine when we should be looking at each of these sites around the world. Once that planning is done, we collect the data with the satellites and then process and validate that data. And then we search through the data to identify emissions if they're there, determine the source location of those emissions, and create the data products that you'll get to see at the end. So the products that you have access to through the CSDA program, the data is available to researchers funded by any US federal agency for non-commercial use through a broad USG and user license agreement. This is intentionally designed to make it easy for you to share the results of your research as broadly as possible. So any derived products that you make can be shared and published. You can use them in your conference presentations. You can use figures in your papers. Please include an attribution to GHGSat if you can, like in a figure caption. The only thing that you can't share are the original data products that you download from the Satellite Data Explorer through SDX. You'll get a zip file full of a bunch of individual files that we'll talk about in the next few slides. Those can't be archived with your journal articles, for example. So in that case, we suggest including a list of the observation IDs for reproducibility if you want to make a list of the data that was used in your publication. Through the CSDA program, you can request new taskings over both single and complex sources onshore and offshore, and we'll go over what that means in the next few slides. So you can place orders through our catalog, which is historical observations that we've already taken, as well as new tasking requests. So asking for a collection of new observations of specific sites. For a single source, this is analysis of the emissions of a specific location within a field of view, so a specific lat-long. And a complex source is 3 or more individual sites to be analyzed in a single image footprint, or complex or diffuse or offshore emissions. You can request monitoring as frequently as once a month, so 12 observations of a single site over a full year, or you can request a single observation if you just want one snapshot at a specific period of time over your area of interest. You can also do some customization there, but the most frequent that you can request through CSDA is monthly. So for the data products in single source versus complex source, the single source emissions, again, like I said, are for a specific site. So an example of this might be an underground coal mine shaft, a specific oil and gas facility, or liquid natural gas storage tanks. Whereas complex sources might be things like landfills that tend to be much more diffuse in their emissions, offshore emissions, more complex oil and gas sites where you have separate emissions over a larger area, pipeline monitoring, or open coal pit mines. When you download the GHGSat data through the NASA SDX interface, you'll get a zip file that has a bunch of different files in it. So let's step through what those are so you know what you're getting. The first is the per pixel sphere surface reflectance. Dylan will go into more detail about what this is, but here you're just kind of looking at the albedo. This is not actually going to show you any of the emissions, but it gives you an idea of where your observation is. Then you have the per pixel methane abundance and error in parts per billion if there are methane emissions detected in the site that you're looking at. So you can see the emissions are highlighted here just to get an example. You also get an error flag in parts per billion if you have the emissions detected. And you get a methane concentration map as a ping. And so that looks like this view on the right. And this is meant for you to be able to just take this and plop it into a presentation or a paper, even as a ready to go figure. It's got the legend on it, and the text down here gives you some of the metadata information. So the latitude and longitude, the satellite with which the observation was collected, the time, and a few other pieces of information as well. You'll also get some metadata in a JSON file. And if there is an emission detected, then you will get this site attributed emission data in the CSV, which will give you the position, the zone, typically the country that this was detected in, the site name, observation, date, the sensor, which is generally going to be a GHG satellite, but if you were accessing other data like the airborne data, it will tell you if that was the source as well. The source rate in kilograms per hour, the source rate error, and the wind speed, because this ties in very closely to how the calculations are done for the emissions. There are 3 different levels of data that you have access to through this. The abundance data set is a level 2 data set, so that's the per pixel abundance in excess of the local background. And so that's another key difference here between GHGSat data and something you might be used to from, say, Tripomi, is that we are not measuring the like absolute abundance that you're seeing over a whole area, but we're looking at the enhancement over the background levels of methane, which is how we're detecting where the plumes are. This data is delivered as a 16-bit geotiff. The concentration map is delivered as a ping. This is level 2. And then level 4 data is the emission rate, which is the instantaneous rate for a detected emission from the targeted source after applying dispersion modeling techniques in kilograms per hour. So I'm going to hand the keys over to Dylan now to go into a lot more of the technical details of how we actually do the processing of the data and the calibration.
So, pleasure to be here. I'll just confirm that you are seeing my screen in presentation mode.
Yes.
Yes.
Great. Okay, so I'm going to give you an introduction to how we make the measurement, some basic physics, how we assess the performance of the instrument, and then some scientific kind of use cases that our data has been used for. So first, we make a measurement by capturing photons from the sun that have been emitted, traveled through our atmosphere, bounced off the surface of the Earth, traveled back to the atmosphere, and then are captured by the instrument. So to do this, we need a model for, well, what's the spectrum of the light emitted from the sun? What happens to the light in the atmosphere? It gets absorbed by molecules, emitted, scattered. And then what does our instrument do to these photons that are captured? And that's what I'm going to spend the bulk of the time on, describing how the instrument measures these photons. But a quick note about units here, because I think it's important to just state explicitly that perhaps what we're most interested in quantifying methane is what the density is, but what this measurement actually does, in any measurement that uses photons from the sun, it measures the integral of the methane density along the photon's path. So our measurable is a column density unit. And sometimes these measurements are expressed in ppb, which might imply a concentration, parts per billion or parts per million, but it's a column averaged concentration value. So it's the ratio of the integral of the density of methane along the photon's path divided by the integral of the density of the air along the photon's path. So you'll see perhaps both of these units in this presentation, but it's the same way of quantifying the same physical quantity, the integral of methane along the path that the photon takes. Okay, so if you were to look inside our instrument and unfold the optical system, you'd see this schematic pictured here. Light is incident from the left, and you have three main lens assemblies, L1, L2, and L3. L1 and L2 are just a telescope. So that means that this larger bundle of light gets focused to a smaller bundle of light. So it can be manipulated through the instrument more easily. And then the last lens, L3, is an imaging lens. It just focuses the light on our 2D detector array. So if all we had in our instrument were these three elements, we just have a nice camera orbiting around the Earth and be able to take nice pictures of the ground. But we have more than that. We have, most importantly, the Fabry-Perot interferometer. And what this is, very basically, is just two mirrors that have highly reflective surfaces quite close to each other. And light that enters into this optical cavity between the two mirrors bounces back and forth many, many times. And so it can interfere constructively and deconstructively. And so any light that then escapes this optical cavity can only do so at very distinct wavelengths. And that's what's shown in this bottom plot on the right. The vertical axis has the units of transmission, and the horizontal axis has units of wavelength. And you can see that we get very distinct transmission peaks at regularly spaced intervals. Just focus on the blue curve, for instance, one of the colors. You can see that we have these very fine spectral transmission features in this Fabry-Perot. And conceptually, that's important because what we want to do is resolve the very fine spectral features in the top of the atmosphere spectral radiance, the light basically that has gone from the sun through the atmosphere and to our instrument. And that's what's shown on the left, the TOSR, this acronym. And so you can see very sharp absorption features here, and these are due to, in this spectral region, solar lines from the sun, CO2 absorption, water absorption, and most importantly, methane absorption. And so the important point is that we have the sharp transmission features in our Fabric Pro that are able to resolve the sharp absorption features that tell us about molecular column density concentrations in the tozer. The one, I just got a polling tweet that popped up. The one other spectral element we have in our system is a bandpass filter, and this just restricts the region of the spectra that we're kind of interrogating. So on the right, you also see that there's not just one color of transmission versus wavelength. There's three, and the different colors corresponds to light that is incident on this Fabric Pro at different angles. And you can see that light that's incident at non-normal angles have transmission features that are shifted to lower wavelengths. And so if we allow a continuum of different angles onto our Fabric Pro, we can kind of sweep with fine spectral resolution over this entire spectra. And that's what we allow. And so the result of this, result of this, let's imagine we were to take a picture of a totally featureless piece of the Earth. This is totally hypothetical. The only signal variation we'd see on a detector would be due to these Fabric Pro transmission modes sampling the absorption features of the spectra. And it shows up as rings because there's nothing that I've described so far that destroys the circular symmetry in this system. So kind of very basically, what our instrument does is it maps wavelength information and the absorption features at different wavelengths onto radius. And we have an instrument model that quantifies that dependence. But that's how you can think of our instrument, mapping wavelength onto radius. So for a real observation, we have not just these rings, but also an image of the ground. And that's what you can see in this leftmost animation. Our observation sequence comprises of about 200 images nominally, where some ground target of interest traverses the field of view. And so that's what the animation shows. Now, at the end of the day, what we want to do is to estimate the column density at each ground location. And so we need to keep track of where each ground location is in each image. And we do this with an image co-registration algorithm. And once we have that co-registration, we can move to the ground frame. And that's what this rightmost animation is showing you. The ground is staying still because we've applied this co-registration algorithm, and it's the rings that are moving. Now, why is this a useful thing to do? Well, if at the end of the day, our instrument model works in radial space, what we can do is plot the signal, for example, at this example ground location, the signal as a function of how far away it is from the center of these rings. So what is its radius? And that's what's shown on the right here. We can then compare this data to our model, which works in radial space. And one of the parameters of the model is the amount of methane, along with some other information. And so what you see on the right is that when this, for low frame indices, when we're at the start of this imaging sequence, this point is quite far from the middle of the rings. So it has a large radius and it moves closer, further away. And we can fit this data to a model and infer the methane concentration. We have a publication that's a few years old now that describes this process in more detail. The output of this, if you were to apply this procedure to the roughly 300,000 or so ground cells that we measure, is an albedo field and a methane field, and some other fields, but these are by far the two most important, you might say. So focusing just on the albedo field at first, while this may look like just a picture of a ground through a funny pill-shaped aperture, this is actually a retrieved quantity. So this only comes out after we've applied the image co-registration algorithm, after we've done this optimal estimation fit to our signal data to a model. But it's reassuring that it does look so much like a picture of the ground. You can see lakes, crop circles, river valleys, roads, ponds, and I'll just point out explicitly the scale of this image. It's about 12 by 16 kilometers. So, simultaneously as we retrieve albedo, we also retrieve the methane enhancement above background. So let me just tell you a little bit about what background means here. So we do estimate the background concentration. And so this is the average methane column density across the whole scene. And for this scene, it was 0.637 moles per meter squared. This is, very close to the global average. This observation was taken in Alberta, Canada in, early March 2021. And the color scale of this image goes from plus minus 0.1 moles per meter squared, or about plus minus 15% of background. And you can see that there's kind of salt and pepper variation everywhere. We've flagged low albedo regions over water, where we don't make a reliable measurement unless we're in a glint configuration, which I'll leave to another talk or questions. But the only prominent feature you see in this image is a small dot in the bottom middle, which I've now zoomed in on. And this is where our ground team was releasing methane at a known rate. And we tasked our satellite to measure this location and in order to see how it was performing. This was shortly after the launch of this satellite. And you can see a nice, enhancement that this plume makes above background. That's reassuring to see. The ground team measured an emission rate of 360 kilograms per hour. Using our satellite measurements and knowledge about the wind, we estimated an emission rate of 388 kilograms per hour, within error. And it's just useful to see what an enhancement from an emission of this magnitude produces. The peak plume enhancement is about 8 times the background error. And a common heuristic is that you can detect plumes when the peak plume enhancement is about 2 times the background error. And visually, this looks about reasonable. So it means that we should probably be able to detect plumes that are about 4 times smaller than this, or around 100 kilograms per hour. We'll establish this more rigorously in the following slides, but this gives you some kind of intuitive image to kind of establish that as well. So I'm now going to talk about some of our calibration and validation procedures and methods that we use at GHGSat. So methane and CO2 and global greenhouse gas imagers, historically before GHGSat and point source imagers, they really had a different use case. They were trying to measure total methane absolute concentrations or column densities. And so in order to validate how well they were able to do that, they compared measurements of the total column to ground-based measurements, so-called TCON measurements at various locations around the world. This is slightly different than what point source imagers are designed to do. We're trying to measure local enhancements above, slightly less local backgrounds. And so quantifying performance is kind of commensurately a little bit different. So we've tried to quantify our performance for these use cases in 2 different ways. One is trying to assess how much our column density precision is. So in small regions where you don't expect, in truth, any variation of methane, how much does our measured methane vary? And that's our L2 product. And then we assess our L4 product, which is our emission rate product, using controlled releases to determine both the detection limit as well as what is our quantification accuracy on our source rate estimate. So I'll go through both of these briefly. So first, do we assess our L2 product, our column density measurement? So as I mentioned before, what we do is we pick a small ROI of about 500 by 500 meters in a region where you don't expect methane to be actually varying. So you stay away from plumes, regions of large gradients, elevation gradients, and we measure the standard deviation of our measurement across this domain. Now, this is also the domain that corresponds to small plumes, and so it's relevant for detection limit. And then the plot on the right shows a histogram. How many times across all of our observations and all regions in each observation do we measure a standard deviation in the methane? And you can see, so the horizontal axis is the magnitude of the standard deviation, either in millimoles per meter squared, that's the bottom axis, or perhaps more intuitively, the percent of background, that's the upper horizontal axis. So you can see that we have a median column density precision of 2.1% of background. Now, this is across all seasons, all terrain classes. There's no cherry picking here. So where does this variation come from? We see this kind of long-tailed distribution. Well, if we plot what the empirical methane noise is as a function of ground reflectance, you can see a strong dependence. I want to mention right off the bat, color scale. This is a 2D histogram with logarithmic color scaling. So we have 100 times more points, counts in each bin that are orange than are purple. So we see the strong kind of inverse dependence where you have lower noise for brighter scenes, suggesting that we're shot noise dependent. We're able to make a more precise measurement over scenes that are brighter. Another way of kind of saying that is when we compare our measured methane noise to a shot noise prediction, it lies pretty close to this one-to-one line. And I, again, want to mention this logarithmic color scaling where, in this plot, there's actually 1,000 times more counts in the orange colored cells than the dark purple. So for the most part, we're shot noise limited. Not quite. We don't want to just make that assumption because there are many cases, specifically around albedo edges, where the albedo changes sharply, where we do have systematic artifacts that we work hard to try and fix. But in cases where we can't fix, we want to at least measure what the uncertainty is due to this error. And so we do this in our per pixel CH4 error estimate. So in each methane, we deliver a methane field where you get an enhancement of a background estimate in each pixel. We also deliver an error estimate in each pixel. And how do we measure this error estimate? Well, we do this using the same optimal estimation machinery that we use to estimate the methane in the first place. So this is a pretty kind of standard framework in the field. And so you can estimate a posterior error covariance. And the kind of perhaps one unique thing we do is instead of assuming an error source to propagate through to our posterior error estimate, and I'm perhaps using some jargon, we actually empirically measure the RMS of our fit residuals and propagate that through. And this means that we're able to capture, real errors empirically. And that's illustrated in these images on the right, I hope. So the top left shows a albedo field for a very complex scene. These are from one of our early retrievals after the launch of these satellites a few years ago. On the right is our methane enhancement estimate. You can see that there seems to be a real methane enhancement estimate, but there's also, some, strong salt and pepper noise, some artifacts, some spatially correlated artifacts. The bottom left shows our methane error estimate using the procedure I kind of briefly described. And you can see that we have high error over regions of low albedo and also regions where this albedo is changing, in this urban area. What's really helpful for instance, one use case of this error estimate is that you can have a signal to error ratio, a kind of signal to noise ratio. If I divide the methane field by the methane error estimate, you get a signal to error ratio, which is shown in the bottom right, which suppresses area with high error, leaving just this one plume, which I believe was from a landfill, the enhancement from it, and making it much easier to detect using this error knowledge that also gets provided. So now I want to tell you about our L4 performance assessments. So this is how we assess how well we're able to detect emissions at different rates and how accurately we're able to quantify our emission rate. So we do this with controlled releases. Currently, there are a number of independently organized controlled release campaigns undergoing, perhaps most notably the Stanford group led by Adam Brandt has been designing controlled release experiments for not just GHGSat, but all a suite of greenhouse gas emitters, both private and public. But this is a relatively recent endeavor, and since the beginning, we've had our own internal controlled release campaigns ongoing. And most of the work has gone towards probing our detection limit. And so for this, we need lots of data, so lots of emission rates at varying magnitudes and varying wind conditions. But I'm going to show you data from both our internal controlled release data, measurements, but also independently organized campaigns. So this plot on the left shows either detections, the blue diamonds, or non-detections, the green crosses, as a function of the true source rate measured on the ground, in the vertical axis, and the wind speed. So you can see that there are more blue dots for higher source rates. And you might be able to see that there's more blue dots for lower wind speeds as well. And briefly, you expect it to be easier to detect plumes in lower wind speeds because the methane that's emitted is not transported away as quickly and dispersed as quickly. It can kind of accumulate. So we have lots of data. These black circle data points are from the independently organized controlled release campaigns we participated in. We will add to these this plot as more of this data is published in peer review. And this is from the Sherman et al. Studies. And we can fit this binary detection data to a model, following the literature that accounts for the wind speed dependence. And the output of this model is a probability of detection at different wind speeds and emission rates. And this is where we get our 100 kilogram per hour, 50% probability of detection at 3 meters per second wind speed. We have a 90% probability of detection for emission rates of 155 kilograms per hour, again at 3 meters per second wind speed. So this is where these numbers come from. We also want to see how accurately, when we do detect an emission, how accurate our source rate estimate is. And so we follow a method that we developed in 2018 that's been published in this Varon et al. Paper. And this plot on the left shows the retrieved emission rate versus the ground truth measured emission rate. And this, again, includes both internal controlled release data as well as independently organized data. And the magenta points are these single blind releases. And you can find the papers for this here. So you can see, generally good agreement. The error bars are quite large, generally on the order of some tens of %. And this is usually dominated by our uncertainty in the wind speed. We just don't know how fast this plume is being transported. We use meteorological reanalysis products and local wind speed when available, but there's uncertainty associated with this, which we try to capture in the uncertainty estimate we attach to our source rate estimate. Yeah, I want to highlight again that we are in constant collaboration with different organizations to assess our products independently, how valid they are, not how valid, how well they work, what the uncertainties are, the detection limits, et cetera, et cetera. We're working with NIST, UN, EP, IMO, NPL in the UK, an ESA-funded Medusa project, quite a few things, and we're always interested in adding to this list of collaboration. The more data, the better for us to, improve our measurements and, more accurately quantify them. So in the last couple minutes, I want to switch to what can be done with our data once, users have information about emissions and non-detections as well at different locations. So in 2023, we saw, now the leading controls are hiding that number, but 16,000 detected plumes or so, and 32,000 clear sky observations. And this is the map of the emissions that we've seen around the world. Currently we have a pretty extensive data set that is about 8 times more plumes detected than any other methane plume detecting mission, and 3 times more plumes than all other missions combined. So it's a very extensive plume data set. We have collaborators at UPV in Spain that has used our data, for example, to detail a gas well blowout. So this is, I think it's published now perhaps, but the Louis Guanter group used our data as well as data from public satellites like Prisma and EMAP and EMIP and others to quantify the emission rate after a blowout event. We've collaborated with the Space Research Institute of the Netherlands and Harvard to study landfills. In one study from a couple of years ago, we tried to quantify the contribution of landfills to total urban emissions at different cities around the world, finding it varied from 5 to 46%. We have another paper in review right now where we quantify, the kind of correlation of methane plumes with surface activity within landfills. It's a nice example of what you can do with high resolution, methane images. With our offshore glint measurement, where we need to pan the satellite at a very specific geometry in order to get enough photon signal off of the water, we measured the Nord Stream 2 leak. That work has been published in Nature very recently. Then we have a paper in review right now where we're estimating oil and gas as well as coal emissions globally with high resolution with our GHGSat measurements in 2023. To give you a sense of scale, these sectors, from these sectors, we've measured over 11,000 plumes from over 3,000 emitting sites. And we estimated about 11% of predicted emissions with our non-complete coverage. And interestingly, at the locations that we did measure, when we compared our emission estimates from our satellites to inventory estimates, which are the best current estimates available, we didn't find that there was great agreement, showing that, satellite informed estimates could be really beneficial to kind of refine, policymaking, mitigation approaches, also just, general kind of knowledge of where emissions are coming from. And with that, I'm going to hand it back to Tanya.
Great, thanks. Okay, so just a couple last slides here to talk about how to actually apply for access to this data through CSDA. So if you go to the CSDA website, there's an authorization request form. You'll need to create a NASA Earth data profile if you don't have one already to put that into the application, and just fill out the form. It'll ask you some questions about things like your grant number and the type of research that you're doing and the data set that you want to get access to. And then once your application is processed by the NASA CSDA folks, you will find out that you've been approved. And then you can start browsing data through the SDX interface. You can search through the archive of previously delivered data from GHGSat in here. It's important to note that this doesn't represent our entire archive of data. It's just the subset that NASA requested during the pilot phase. So even if you look here at a site that you're interested in and you don't see any data in SDX, that doesn't mean that there's not any data there. This is a very small subset. So definitely reach out to us if you're interested in finding out if there's archive data over an area of interest. If you want to request tasking data over a new place where we don't have any observations, or a place where you just want to collect future data and we do have historical observations, you submit those requests through the CSDA team as well. And then we can do a feasibility study to figure out what the timing would be for getting that data to you. We're going to be launching a science newsletter soon to showcase more use cases for the data that come out of the research community. If you do something with our data, we would love to include it in the newsletter. So please let us know what you're working on, and we'd love to include it. You can sign up through a link through this page here. This QR code will also be accessible after the fact through the link that's posted in the chat for these slides. So if you don't have a chance to scan it right now, you can scan it later. And with that, if you have any questions, you can reach out via email or feel free to put them in the Q&A now, and we will go through them here live as team.
All right. Well, thank you so much, Tanya. At this point, I'm going to open the final optional set of polling questions and then skip directly into the Q&A session. Let me go ahead and open the final poll. All right, you should see that. And I am going to, some of the questions have been responded to by Dana within the Q&A. And so your first question here is, how is the background of methane derived?
It's derived in the same way that the enhancement is derived, except that we average the spectra basically from all ground cells and then fit a model to that. So it's the average concentration over all ground cells.
Well, thanks so much, Dylan. And your next question here is, if we have any problems accessing the data, Tanya, can we reach out to you?
Yes, absolutely. We're here to help with anything that you might have questions with in terms of access, processing. If you need help with content for proposals, if you want assistance with some of the technical details of the data, you can ping us for all of that kind of stuff. We're here for you.
All right, thank you so much, Tanya. And let's see, just scanning. See if there are any. There were a couple of questions where participants were asking about the, the timing for the NASA CSDA on-ramp RFP being released toward the end of the summer. And Dana Ostrenga did respond that yes, they are still anticipating to follow that schedule. More information should be coming out soon. Let's see here. I just want to make sure I'm not missing any questions.
There is one, Jennifer, about the air maps. I don't know if I missed that.
About the, let's see here.
In the chat for target emissions during air maps over the Baltimore-Washington region.
Okay. Oh, I just see that, yes. Okay, so are there plans to target emissions during air maps over the Baltimore-Washington region?
Not that I know of. The bulk of our kind of coordinated emission monitoring is with controlled releases, although we have various kind of other campaigns that we do with collaborators, but I haven't heard about that one.
Okay, well, thank you very much. And then there's a follow-on question by the same participant. Has your team examined the Baltimore-Washington region? I understand that the urban surface will be a problem.
Sorry, I didn't quite catch that. Oh, so I guess
Yes. So
we are
yes.
doing some.
Yes, and so the final question by the same participant is, has your team examined the Baltimore-Washington region? I understand that the urban surface will be a problem.
Eric, do you know about the AirMap campaign that we may be collaborating?
I actually think I saw Gunther from NOAA in the audience.
Yes.
So maybe she can comment on this. We did do some observations on behalf of NOAA of a coal pile in Baltimore Harbor shortly after the tragic events of the bridge collapse. So I don't know, maybe Shobha could comment on that perhaps.
Yes, and then there is actually a follow-on. If people could post their questions in the Q&A panel, that would be very helpful. But in the chat, there is a follow-up. I am one of the leads of Air Maps. We intend to work with GHGSat through our contract with NESDIS. And then to the next question, is there a cost structure associated with requesting satellite looks, or is this free for government agencies?
So the access to the data is free through CSDA. So you don't have to write in the cost into your proposals. You already have access through this program.
Wonderful. Thank you so much, Tanya. And then I'm just scanning to see.
I did see a question about whether the urban environment would pose challenges.
Yes, I
in
did.
general,
I did pose that question already. Yes. That's
yeah,
okay,
so I didn't quite answer it. The answer is yes. The more complex the albedo scene, meaning the more, the reflectance changes, generally the harder it is to make, a precise measurement. This is mitigated, somewhat, given our error estimate. That should hopefully, help, qualify how good a measurement is at each location. And using something like a signal to error ratio, it should try to normalize for this. But we do have to assume certain things. For instance, that you have, for instance, Lambertian reflectance, which is generally true across the ground, but in an urban environment, you might have more specular behavior and other more spectrally dependent behavior that does make these measurements in general more challenging than over a desert, say.
Well, thank you very much for the additional information there. Okay, so there are a couple of questions. And just as a reminder, if you could please add your questions to the Q&A panel. If you don't see that, click on the 3 dots at the bottom of your screen, and you should be able to insert a check mark next to the Q&A panel. So the next question is, what about future campaigns to request satellite data? Is this something that will need to be coordinated ahead of time?
Yeah, so you'll have to submit the requests through CSDA with the time range that you're interested in and the lat-long locations that you're interested in. And then we use that to run a feasibility study to make sure that we can collect the data over the area and time that you are interested in. And if for some reason we can't, then we can work with you to figure out, can we change the parameters some way to still get the data that you're interested in?
Okay, thank you so much, Tanya. And so the next is not a question, but more so a follow-up to the conversation earlier. I think the coal pile situation was different. No, not high enough to be detected, but landfill emissions in the Baltimore area were also not picked up. We should revisit this under air maps. All right, and if you will bear with me while I conduct another scan of the chat first and then hop down to the Q&A. So if you submit something into the chat while I'm looking at the Q&A, it will take me just a second to get to that one. Let's see here. I don't see anything in the chat that was missed. And looking down to the Q&A. All right. Well, while we are waiting to see whether or not there are any additional questions, I just wanted to say a word or two about the recording and also the presentation slide decks. And so we have recorded this afternoon's event, and it takes 2 to 3 days or so for webinar post-processing, but I will, once that has been completed, the event will be posted to our NASA Earth Data YouTube channel. There is a commercial satellite data acquisition program specific playlist, and then it will also, that information, a link to the recording as well as to both of the presentations that were provided during today's event will be emailed to all registrants as well as participants. So if you have any colleagues who registered but were unable to attend, they will receive information to review this content at a later time. And so let me do another look here. I don't see anything that I'm missing from either the chat or the Q&A. So with that, what we will do, I'll give it another couple of minutes or so, but what I'll do is log off from the audio component of this event, but I will leave the virtual meeting space open for an additional 10 minutes or so. So if you think of a question for our speakers or for the CSDA program, please feel free to enter that information in the
So I do see a question
yeah, I do. I
on the
see it.
chat from
I
Aaron.
I see another question here. Okay, so, yep. So the question is, I'm not sure if that's the question you're referring to. What level of confidence do you have in emission rates from plumes in complex scenes with multiple potentially mixing plumes? Any controlled releases with multiple plumes in a single scene?
Yeah, so the answer is controlled release we don't have any controlled release data for plumes, multiple plumes that are mixing to see the effect. What's our level of confidence? We try to, obviously we distinguish plumes, based on their origin. And then, in the case of mixing plumes where the tails start mixing, then it becomes, kind of an operator judgment about, what part of the plumes to use for the emission rate quantification from each, individual source. And so then, the level of confidence therefore kind of depends on, kind of what portion of the plume, is separate from, the mixing portion. So that's kind of the short answer is it depends. Often it can be, probably we're still going to be dominated by wind uncertainty even if we have some tails of some plume mixing downwind, because we can just use the, further upwind portions of the plume to make an estimate. But yeah, it depends.
Well, thank you so much for your response, Dylan. So there's another question that was just added to the chats. I'm an economist who is interested in facility level emission data at a global scale over time. How many years of data are available at the facility level around the world?
This might be a question for Tanya. I'm not sure how far back we are providing data.
They can request anything in the archive.
Mm-hmm. So then the kind of the answer is we launched our demonstration satellite in 2016. It didn't have great performance. So meaning the detection limit was, quite a bit higher than 100 kilograms per hour. And then our next kind of first commercial satellite was launched in September 2020, I believe. And then our kind of latest iteration was launched a few months later, and C2 and onwards, have the kind of the best performance, and they've been operating since 2021.
Thank you both. So we do have another question. Have you compared methane plumes from Carbon Mapper 4 and fills lots of data.
The question is, have we compared our landfill measurements from GHGSat to Carbon Mapper average landfill measurements?
Yes, that's I could one could make that assumption. There was a typo there. Yes, you could. Great.
I haven't personally compared our landfill measurements to Carbon Mapper landfill measurements. You might be referring to this, the California landfill measurement paper. I think it was just from California that was published last year. We do have the landfill measurements that we have compared to our landfill measurements that we've compared them to TRPOMI estimates, but those are over urban emissions, also inventory estimates. So I guess we've been working on a global scale for landfills. And so we've been, targeting individual landfills, but all across the world. And so our analyses have been kind of compared to data sets that are kind of available kind of globally. These have been inventory estimates for the most part. It's an interesting question, but we haven't done a kind of comparison of landfill measurements in California to those measured by, Carbon Mapper Avarice.
Well, thank you for your response. To see if I have, as of this moment, all of the questions in the Q&A have been addressed. And let me jump back up to the chat just to confirm that we have addressed those as well. Don't think we're missing any questions. Okay, so getting back to what I was saying a bit earlier, yes, we will log off from the audio component and we'll leave the virtual meeting space open an additional 10 minutes from end time. And so if you think of something, feel free to enter that into the Q&A or the chat, and we'll be able to have the speakers follow up with you offline. All right, looking one more time. Make sure I haven't missed anything. I don't think so. All right, so with that, I would like to thank our Q&A panelists, Lars and Johannes, and also our speakers from GHGSat, both Tanya and Dylan, and then our CSDA program speaker, Dana, for your time this afternoon, and to thank all of you for your feedback on the optional polls and also your time with us. Let's see here. I think that's it. Just doing one more quick look. All right, well, with that, thanks everybody. We'll log off from the audio component and I will leave the virtual meeting space open. All right, thanks everybody. Goodbye now.